This is PreCalculus 12, Chapter 6.4. We're going to be looking at graphing trig functions. And we want to keep the idea that they're cyclic. That means they repeat. They go in cycles, and it's best to use radians. So here we have a graph of y equals sine x, y equals cos x, y equals tan x. So you should understand these shapes. Sine starts at 0, goes up, goes down, back to 0, and this is one cycle. And the length of one cycle is called the period. And this is 2 pi using radians. It's important to note that sine starts at 0 and goes up. Here we have a 0 and goes down. That's halfway through the cycle. So sine is always 0 and goes up. Cosine starts at 1, comes down to -1, and comes back up to 1. Tangent, it doesn't start at 0. It actually starts at -pi/2. And it's cyclic, so we could start from here at pi/2. It's the same as -pi/2. It starts at -infinity, comes up through 0, and goes to +infinity. And the length of this period is pi. And the length of cosine, its period is also 2 pi. And again, this is the length it takes to repeat. You want to note here, this is the vertical asymptote, and it's an NPV, so not in domain. And we can understand this if we look at the identity for tangent. Tangent is y/x, and that is sine theta over cos theta. And the NPVs are where cosine theta equals 0, because we can't divide by 0. And here we have the inverse trig functions. And before we look at these, let's take a look at Desmos. So here is our sine function. Here's our inverse sine relation. And it's a relation because if we draw a vertical line, it passes through more than one point. What we would like to have is an inverse function. Let's turn on these segments. So we're going to limit the domain into segments, and we'd like to determine which segment gives us a segment on our inverse relation that will give us a proper range. So this one matches up with this one matches up with this one matches up with this, and this one matches up with this. So there's many choices, and the right choice, so this one is not the right choice, and this one is not the right choice, and this one is not the right choice. This is the right choice, because it gives us this as the range. And why are we interested in this as the range? Well, because this part is our reference angle. This part is our reference angle as well. And we can't go from the reference angle this way because, again, this is a relation and not a function, and we'd have to include up to here to get our negative values. And if we go on this segment, it gives us our negative values. And we can make the same argument for determining the domain for cosine and tangent. So let's go back to our document. So sine goes from here to here. It includes our reference angle, and the domain is -1 to 1, and it gives us a range of -pi/2 to pi/2. And it looks like this. For cosine, starts at 1. We want this part, and we want the negative part, so we go this way. If we went this way, we would get more positive parts, and it would not be a function. It would be a relation. So we don't really have a choice. We have to go this way to do our inverse cosine. So our domain, again, is -1 to 1, and our range is 0 to pi. And if we graph it on a unit circle, it looks like this. If we graph this on the unit circle, it looks like this. And tangent, again, we want the reference angle, and it doesn't connect to this part, so we'll have to go backwards. So the domain for inverse tangent is all reals, and the range is -pi/2 to pi/2. Okay, so its answer is similar to sine. And again, we want to note quadrant 1 is common for all three, and that's again for our reference angle. And if you always just do the reference angle, I think you'll have an easier time to solve problems. Okay, let's look at an example. Find theta in quadrant 3, where sine theta equals -0.5. Okay, so -0.5, our radius is 1. This is theta prime. And we want to find exact. So theta prime equals pi/6. And if you need to work in degrees for now, 30 degrees. Theta equals pi plus theta prime. So we have pi plus pi/6. And we need a common denominator, so we multiply this by 6/6. So we get 7 pi/6. And in degrees, this is 180 plus theta prime, 180 plus 30, that's 210. And on our calculator, inverse sine -0.5, we would get -30 degrees. But what we should do is theta prime equals, and we'll do inverse sine of 0.5, do the absolute value. We get 30 degrees. We have our reference angle, and then we can go through the calculations. If you did this in radians, go into radians. And if you have a smarter calculator, it will actually give you it in terms of pi, -pi/6. But again, we want the absolute value. And we get pi/6, and we can proceed with our calculations. If you do this on a graphing calculator, you have answers here, 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 here. And you see that sine is negative here and here. We can ignore these because these aren't principal angles. This is not principal angle. It's always important to give your answers within the principal angle if you're not specified. Here, this is quadrant 3. This is quadrant 4. We know this because of all students take calculus. It's negative in 3 and 4. And we want the first occurrence because we're looking for the answer in quadrant 3. And then you would have to do a solve on your calculator here. And don't search for this point because that's in quadrant 4. Here's another problem. Find theta in quadrant 3 where cos theta equals negative 0.5. So theta prime, this is 1, and this part is negative 0.5. And again, we want an exact answer. We notice this ratio is a special ratio. So theta prime equals pi over 3. And again, in degrees, this is 60. So theta equals pi plus theta prime. This is pi plus pi over 3. We need a common denominator. We multiply this by 3 over 3, so we get 4 pi over 3. In degrees, we have 180 plus theta prime. This is 180 plus 60, and we have 240 degrees. And again, on our calculator, if you do inverse cosine of negative 0.5, we get 2 pi over 3. So this is in quadrant 2. You're going to have to do some calculations to get the quadrant 1 answer. So again, it's best to do the positive value inverse cos of 0.5, 2 pi over 3. If we do the reference angle, you get pi over 3, and you can proceed with your calculations. Again, if you're going to solve this on the calculator, you have answers here, 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 here. We look at this. All students take calculus. It's negative in quadrant 2 and quadrant 3. So we're looking for the second answer, which is in quadrant 3. The first answer is in quadrant 2. So this is not the one you want. Next example, find theta in quadrant 2 where tan theta equals negative 1. Theta prime, we have 1, we have negative 1. Theta prime equals pi over 4. Again, special angle, we want to find an exact answer. Theta equals pi minus theta prime. This is pi minus pi over 4. We want a common denominator. We multiply this by 4 over 4. So this is 3 pi over 4. This is 45 degrees. And in quadrant 2, it's 180 minus theta prime. 180 minus 45. We get 135 degrees. Looking at our calculator, if we do inverse tan of negative 1, again, this gives us negative 1/4. We can't use the formulas. Pi over 4. Our reference angle is pi over 4. We want to use inverse tangent of 1, and we get pi over 4. And then we can go ahead through our calculations. And if you were doing this on a graphing calculator, you have answers here, 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 here. So we look at this. This is quadrant 1. This is quadrant 2, quadrant 3, quadrant 4. This is our quadrant 2 answer. This is our quadrant 4 answer. We know it's negative in quadrant 2, and we know it's negative in quadrant 4. So we need to look at the first answer after our y-axis. And you have to be careful. These are not answers. These are the vertical asymptotes. And anytime you see a steep line, you have to check to see if it's a vertical asymptote. So not solutions. And here are the formulas in radians. So going from standard angle to reference angle, and going from reference angle to standard angle. It's the same formulas, we just replace pi for 180 and 2 pi for 360. And that completes this lesson.